Bismillahirrahmanirrahim. Today we are going to discuss about the Wien's displacement law. What is this law about? So this law states that the wavelength of electromagnetic radiation emitted by a body is inversely proportional to the absolute temperature of that body. As the temperature increases, the wavelength of emitted radiation becomes shorter. And we can also say that this law tells us that objects of different wavelength emit spectra that peak at different wavelengths. So what does this mean? If we look to this animation, and if I increase the temperature of a body, so this wavelength is shifting towards the shorter wavelength like this. So this at a particular wavelength, this is the peak wavelength. Now if I increase the temperature, so this peak will shift towards the left side of the ultraviolet region like like this. So what Wien's tells us about this graph, that the lambda, which is associated with each temperature, so this is lambda and this is a maximum one. This is directly proportional, this is inversely proportional to the temperature. So this means that as we increase the temperature like this, so the wavelength is going to be shorter and shorter like this. From this, if I use the constant instead of this proportionality, so the lambda max is equal to, I will use this constant b divided by t, and the value of b is equal to 0.0029, and this is meter, and the temperature is Kelvin. So this is a constant value. We can also write this equation as lambda max multiply t, which is equal to constant, and this constant is this value. So we need to understand that what does this mean. So we can also define the Wien's law, that it tells us that the maximum lambda and the temperature, the product of these two will becomes constant. So if we look to this again, so if I want to find this constant, that what does this constant mean? So I have 0.651 micrometer, this is in micrometer, so I need to multiply this with 1000 to becomes nanometer. So I will first multiply this with 1000, and then I will multiply with this temperature 4450 Kelvin. So we need to check whether this gives us this 0.0029 Kelvin, 0.0029 meter Kelvin or not. So let me calculate this with my calculator. So this is 0.651. So we need to multiply this with 1000. This is 1000, so this becomes 651, and this is 651. This is 651 times 10 to the power minus 9 meter. So this is nano. Now I want to multiply this with 4450. So this will become multiply with 4450. So let me multiply this 10 to the power minus 9 multiply 4450. So we can get approximately 0.0029. So we got this value. So now we need to check for another value, like this is the temperature of the sun, and this is the peak lambda, which is equal to 0.483. Again, we need to multiply this with 1000. So this is 0.483 multiply 1000. So this becomes 483, or this becomes 483 times 10 to the power minus 9 meter. So I will multiply this with now this temperature 6000. So this is multiply 6000. So this is again going to be 0.0029. So this means that this value is a constant for every multiplication of lambda max and a temperature T. This is the meaning of this constant. So if you multiply this 0.604 with 1000, so you need to convert this with to convert to the nanometer first, then you can multiply this to 4 to this temperature, any temperature. So you will get this value like this. So that's why Wien's say that when you multiply the maximum lambda, maximum wavelength, and the temperature, so you will get a constant, and that constant is equal to 0.002. Now if we look to another example, like this is the example. For example, a star whose surface temperature is 11,000 Kelvin. So what is the wavelength in nanometer? So we can find this like this is lambda max, and this is equal to, we know the constant, this is 0.0029. So we will divide by the temperature 11,000, and this is meter Kelvin, and this is Kelvin, so this can cancel, and this lambda max is equal to 0.000, and this is again 000 and 263, so which is equal to, in the scientific notation, 2.63 times 10 to the power minus 7. So since we know there are 1 billion around, this is billion nanometers and meter. So we simply multiply our answer by 1 billion to convert it from meters to nanometers. So this is 0.00000263 times 1, and this is 0.0000000, and this becomes 263 nanometer. So what color would we see with our eyes? For this, the answer is that the wavelength is 263 nanometers, and this is in the ultraviolet part of the electromagnetic spectrum. So our eyes cannot really see any wavelength smaller than around 400 nanometers. So we would not even be able to see this light. This is this electromagnetic radiation. So Now we can check another example, like what is the surface temperature of the star whose maximum intensity is 400 nanometer. So we again know the formula that lambda max is equal to the constant 0.0029 divided by the temperature in Kelvin, and this is meter Kelvin. So for our solution, I can write 400 because this is 400, which is equal to 0.0029 divided by t. So we can rearrange this. T is equal to 0.0029 divided by 400. So we can convert this to nanometers, like we will convert this value to nanometers. Then the temperature is equal to, this is the temperature, which is equal to 2900 and 000. This becomes nanometer Kelvin divided by 400 nanometer. So we get the temperature of around 7250 Kelvin. Can find the temperature of any body. So this is a little hot than our sun, and the wavelength is 400 nanometers, would be at the violet end of the spectrum. As we have learned, the hotter the body or hotter the star, the smaller the wavelength in nanometers, which relates to color towards the ultraviolet end of the visible spectrum. So finally, we can say that this is the graph for which Wiens want to explain the spectrum of the black body radiation. So this is the experimental, this is the observed value. Later Planck solved this issue, and this is the Rayleigh-Jeans calculation. So we can say that Rayleigh-Jeans, for this calculation, what Rayleigh-Jeans did, Rayleigh-Jeans explain, I can write this down here. So Rayleigh-Jeans explain low frequency means large wavelength, and we can also say that the Rayleigh-Jeans fail to explain the high frequency means short wavelength. Now the Wien's displacement law, Wien's law successfully explain the high frequency. The high frequency means short wavelength, short lambda, and he failed to explain the low frequency means large lambda. So here we can see this Rayleigh-Jeans explain low frequency and meaning large wavelength, and failed to explain high frequency and short wavelength here. So this is the observations for Rayleigh and Wiens. So now this curve is successfully explained by the Planck's. So we will discuss in our next lectures.